In this lesson, we will explore the characteristics of graphs of rational functions and analyze their behaviors. Now, when we explore graphs of rational functions, there are certain behaviors and properties that we want to bring to your attention. One of the key ideas we're going to be exploring are vertical asymptotes. So vertical asymptotes are vertical lines which corresponds to the zeros, the x-intercepts of the denominator after simplifying the rational function. So again, those values of x where the denominator is equal to 0 on a graph that is represented by a vertical asymptote. So to find the vertical asymptote, we're going to set the denominator to 0 and solve for the variable. So as an example here, we have g at x is equal to negative 2 x minus 1 over x. X, the denominator, cannot equal to 0. That would result in the function being undefined. That value of x is where we have that vertical asymptote. And again, the vertical asymptote is a real vertical line at that value where x equals 0. If we look at k at x, we have 8x plus 1 over 2x minus 6. If you look at the denominator, if we set 2x minus 6 equal to 0 and solve for x would equal to 3. So when x is equal to 3, our denominator is undefined. So if you look at that graph, you can see that at x equals 3, there is a vertical line where the curve gets close to it, but it never crosses it. Another key concept we're going to be looking at is the horizontal asymptotes. A horizontal asymptote is a horizontal line that describes the activity of the rational function for extremely large values for x and extremely small values for x. To find the horizontal asymptote of a rational function, we simply compare the degree of the numerator, n, to the degree of the denominator. So there's 3 different cases we will be exploring. If the degree in the numerator is less than the degree in the denominator, there is a horizontal asymptote always at y equals 0. So an example of that is f at x is equal to 2 over x plus 1. The degree in the numerator would be 0 because 2 is a constant. Degree of any variable, if you remember, is the exponent on your x. So the highest term is exponent represents the degree of that polynomial. So when you have a constant 2, that means the degree here, there's no variable, is 0. If you look in the denominator, we have x plus 1. Well, the degree of that polynomial is 1 because the exponent on x, the highest degree term, is 1. So that means the degree in the numerator, 0, is less than the degree in the denominator, 1. So therefore, there would be a horizontal asymptote at y equals 0. So if you notice, the curve gets closer and closer to that x-axis, but it never touches it or crosses it. The second case would be, if we look at our second case, we look at the degree. The degree in the numerator is greater than the degree in the denominator. In this case, your rational function would have no horizontal asymptote. So an example of this is like f at x is equal to x to the power 4 minus 1 over x plus 1. The degree in that numerator is 4 because the highest exponent on x is 4. And in the denominator, it would be 1. So even though we don't see the number 1 on top of that exponent for x, we know it's there. 4 is greater than 1, so therefore the degree in the numerator is greater than the degree in the denominator, so therefore there is no horizontal asymptote. The third case would be the degree in the numerator is equal to the degree in the denominator. Well, in this case, to determine the horizontal asymptote, that equation is y equals the leading coefficient of the numerator divided by the leading coefficient of the denominator. So for example, we have f at x is equal to 6x plus 1 over 3x plus 2. The degree in the numerator is 1. The degree in the denominator is 1. So therefore, the horizontal asymptote in this case would be the leading coefficient in the numerator, which is 6, over the leading coefficient in the denominator, which is 3. So y equals 2 is where that horizontal asymptote would be. So if you see here, that's exactly where it is shown. Y is equal to 2. The curve gets closer to that horizontal asymptote, but it never crosses it. Right? Note, there is a fourth case when the degree of the numerator is greater than the degree of the denominator by exactly 1, but the method of determining this type of asymptote is beyond the scope of this course. That's called an oblique asymptote, just for future knowledge. Okay, another behavior we want to look at are holes. Holes are undefined points on the graph that occur where the denominator equals to 0, but the numerator and the denominator have a common factor and they cancel out. They are points that make the graph of the function discontinuous. They are represented on the graph by open, dot, or circle. So we will be exploring all these properties and behaviors of rational functions. So let's look at example 1. We're going to determine whether the graph of the rational function has a vertical asymptote, a horizontal asymptote, a hole, or neither. And then we're going to use that information to do a quick little sketch of the graph. So as we did previously, we do always want to factor to see if we do have a common factor, which would result in a hole. Once you've simplified your rational function, if you have a value or an expression in the denominator that results in the rational function equaling 0, the denominator of that rational function equaling 0, that's when we have a vertical asymptote. When we're looking at the horizontal asymptotes, we're looking at the degrees, but we always want to fully factor first and simplify. So let's start with f at x is equal to, again, that's a difference of squares. So it's going to be x plus 1, x minus 1, all over x plus 1. Okay, so keep in mind, if we simplify a common factor, that would be a whole. Anything remaining in the denominator after you fully simplified, that is a vertical asymptote. Horizontal asymptote exists depending on the degree of the numerator compared to the degree of the denominator. So in this case, we have a common factor of x plus 1. Because we have that common factor, we're going to simplify. So we're going to take x plus 1 divided by x plus 1. Anything you factor as a common factor, this is going to be a whole. Just as a reminder, at x plus 1 equals 0, x is equal to negative 1. Okay, that's where our whole is going to be. And again, representing it on our sketch, there would be an open circle where x is equal to negative 1. So then simplifying, we have f at x is equal to x minus 1. So interestingly enough, we have simplified this rational function because we did have a common binomial factor into a linear function. Okay, but it does have a hole. The hole is at x equals negative 1. But because we have to draw our hole, we want to make sure what is the corresponding y value so that we have an accurate picture of the hole. So in this case, in order to do that, we take the simplified function and we sub in negative 1 to find out what the corresponding value of y would be. So even though we simplified into a nice linear function, we need to make sure that the whole exists at that point when f is negative 1, y is negative 2. Okay, so looking here, do we have a vertical asymptote? No. So vertical asymptote, we can say none. Okay, do we have a horizontal asymptote? None. Do we have a hole? We do. A hole at x is equal to negative 1. Okay, so keeping in mind we do have that linear function. So my slope in this case is 1 over 1, so rise over run. And then my y-intercept is negative 1. So we start at negative 1, up 1 over 1, up 1 over 1, up 1 over 1, up 1 over 1. Now, keeping in mind, we do have a hole when x is negative 1. So when x is negative 1, we're going to have an open circle indicating that the function does not exist at that point. So taking a ruler, we're going to connect our line, keeping in mind the function exists up until that point, but not at that point. Which is, you can put the original or the simplified. Okay, moving on. We have f at x is equal to 1 over x minus 3. Now, we can't simplify that any further. So that means the function's already simplified. The value of x that results in the denominator equaling 0 would be our vertical asymptote. So in this case, a vertical asymptote does exist. We're going to let x minus 3 equal to 0 and solve for where x is equal to 3. So that's where a vertical asymptote is. And again, a vertical asymptote would be a line at x equals 3. So we would draw ourselves a vertical line. Excellent. To help us sketch our resulting rational function. So x is equal to 3. Okay. Do we have a horizontal asymptote? We have to look at our conditions. Looking at the degree in the numerator. So degree in numerator and numerator is 0 because there's no variable in the numerator. So that means the degree is 0. And then we look at the degree in denominator, which is 1. So therefore, the degree in the numerator is less than the degree in the denominator. So we know that there is a horizontal asymptote at exactly y equals 0. That is the condition, the first case we looked at. That always happens when the degree in the numerator is less than the degree in the denominator. So we can draw ourselves a horizontal asymptote at y equals 0. And don't forget to label that asymptote. Okay, and we just want a quick sketch. We know the reciprocal function has those key points at -1 and -1, when x is -1, y is -1, and 1 and 1. But we underwent a horizontal translation right 3 units. So if we take those key points and we know that we're going to have our curve in this section and then a curve in this section. We're just doing a quick little sketch. Okay. Hole, there is no hole. Looking at C, we have f at x is equal to 2x squared over 2x squared plus 8x. So we want to fully simplify first. So looking at the denominator, we have a common factor of 2x over x plus 4. Good. So looking here, we can simplify. We can take 2 divided by 2, which is fine, but we want to keep in mind, if we take x squared divided by x, we're left with x in the numerator all over x plus 4. Once we simplify, we want to keep in mind all the different properties we're looking for. So vertical asymptote, again, is in the denominator, there is a value of x that would result in it being 0. So we set it equal to 0 to the denominator x plus 4, and we solve for x. So x is equal to -4. That means we have a vertical asymptote at x equals -4. So we draw ourselves a vertical line at x equals -4. We label that as x equals -4. So vertical asymptotes exist there. Horizontal asymptote. We know a horizontal asymptote exists, and we have to compare the degree of the numerators to the degree of numerator, and that is 1. Remember, keeping the exponent. The degree is the exponent on our highest variable term, and this is x in both cases. And we look at the degree of denominator, and that is also equal to 1. So that means you're equal to, that was case number 3. So if the degree of the numerator is equal to the degree of the denominator, the horizontal asymptote exists at the leading coefficient in the numerator, which is 1 over 1. So that means we have a horizontal asymptote when y is equal to 1. So y is equal to 1, we're going to draw ourselves a horizontal asymptote. Right, y is equal to positive 1. And that's going to help us sketch what this curve is going to look like. The other property we're looking at is any holes. Now, if you see here, we factored an x squared divided by x, there was an x there. So there's a hole at x equals 0. So again, to find the corresponding y value, we would substitute that in the simplified form, which is 0 over 0 plus 4. So f at 0 is equal to 0 over 0. F at 0 is equal to 0. That means we have a hole at 0 and 0. And that's going to help us sketch this. And that's all we want. We know according to any rational function. Okay, and then there is a reflection in the opposite quad, we can say. Okay, and that would represent the function f at x is equal to 2x squared over 2x squared plus 8x, which includes a vertical asymptote at x equals -4, a horizontal asymptote at y equals 1, and a hole at 0, 0.